Alright, hello and welcome to AIAIART Lesson 2. I did manage to record the live lesson, but unfortunately we had enough connection issues and glitches that it ended up being a lot of, can you see my screen, what's going on? So I thought rather let me re-record it smoothly through without the benefit of the live interaction, but with the benefit of offline recording so that we're not bugged by the same network issues that caused trouble there. So lesson 2 is going to be building very much on lesson 1. So if you haven't already seen that, I'd recommend at least checking out the notebook, if not watching the video run through of that as well. So in lesson 1 we looked at some PyTorch fundamentals, how do we create and manipulate tensors, indexing, loading images and so on. And then we introduced this really key idea, which is gradient descent. Right, if we have a function that is differentiable and controlled by some parameters, we can optimize those parameters using this magical algorithm called gradient descent to gradually improve it over time by looking at how our loss, our measure of how badly it does, how that loss changes, in other words, the gradient of the loss. So really cool algorithm. We tried it first with a very simple function, right, a straight line with 2 parameters. And then later we said, well, if we treat clip as this magical black box, right, using it to measure similarity between an image and text, we could treat all the pixels of the image as parameters, and with a few tweaks we could optimize such that we get closer and closer to something that looks like an actual image. So 2 drastically different applications of gradient descent there, and right at the end we also looked at different optimizers and improvements. But what we didn't do in that whole first lesson was talk at all about neural networks, and this is an AI art course after all, so we're going to fix that today, and we're going to look at, first of all, how do we construct basic neural networks with PyTorch? What are some of the innovations that have led to more modern, specifically convolutional neural networks? And then how do we use these neural networks artistically? So looking at the kinds of representations that they learn and what those mean for us. So let's dive in. I'm going to be running a copy of this notebook, so I recommend you do that as well so that you can make changes and have them persist in your drive. So first thing is going to just download or import some libraries as before. This is the code from lesson 1. A few extra libraries, which we'll talk about as they come up, specifically a way to load a pre-trained model, some data sets and transforms from Torch Vision, and then finally also downloading a data set, which again we'll use for some of these examples. Right, once that's run, I'm actually going to recommend that you pause this video and watch the embedded video here. I found there is some great content from the Neuromatch Academy, which I think is also linked in full somewhere else in this notebook. But this is just going to give an introduction to the topic of today, building neural networks with PyTorch. So rather than me rehashing their video, you can pause this one, go and watch the embedded video, and then come back once that's done. Okay, so if you did watch that, or if you'd like to just skip forward, it basically introduced this idea that although we could manually create various different sort of layers and neuron types and so on ourselves, PyTorch has a lot of built-in building blocks to make defining our function, i.e. our neural network, really easy, as well as built-in loss functions and built-in optimization methods. So it really provides us a lot of the building blocks to do these kinds of tasks without having to do everything from scratch. So to demonstrate this, we're going to fit our own simple neural network on some made-up data. So this cell here is going to generate the data, and you can see here there's some sort of relationship between the input, in this case just one input, x, and the desired output, y. So how do we define a neural network? Well, like the video they showed, or the PyTorch documentation will show, we can define it by, first of all, inheriting from nn.module. And this is going to give us a lot of extra features built in. We're not going to have to worry about all of the nitty-gritty details. So you can see there's a bit of documentation if you hover over it. So we need to define a few things. We need to initialize our network, i.e. tell it how to create it, what layers are we going to use, and so on. And then we need to specify what path the data is going to take through our network. So in this case, we're constructing a linear network, right? Something similar to the diagram shown on the thumbnail of this video here, but with one hidden layer. And so we're going to stack a linear layer that has one input and some number of outputs. In this case, we're saying number of cells or number of hidden neurons is 512. And then for a network to be able to learn complicated patterns or to be able to go deeper than one layer, we need to introduce some sort of nonlinearity. So again, there's many on offer in PyTorch. For this example, we're going to use the tan H nonlinearity. Common options might be like a sigmoidal function or just rectified linear function, ReLU. And then we're going to have a final sort of output layer that's going to take in 512 inputs in this case, the outputs from our hidden neurons, and it's going to create one final output, and that's going to be the output of this network. And we could manually pass the data through these layers one by one, but we're going to make use of PyTorch's nn.sequential, which is going to feed these through the output of each layer into the input of the next layer. So that's going to handle all of that for us, and it's going to mean that in our forward method, we can just call self.layers, which is this nn.sequential object or module, which is going to handle these, it's going to stack these three layers together. So this is our definition. Let's create one and investigate it. So you can see here I'm using our new class, creating an object of type wideNet. And then we have some inputs, right? The same inputs that we generated rather in this cell. And so we're going to pass those through the network. Now we could call wideNet.forward and then pass in our data. But as a shortcut, we can just call our wideNet like a function. And this is going to, by default, pass it through the forward method if that exists. So a little bit of PyTorch magic to make our lives easier. And we can see in this case, for 64 inputs, we have 64 outputs, because for each, rather, we have one input in a batch size of 64, one output for each of those batch size of 64. So that's pretty nifty to see that it is doing what we expect. It's mapping one input to one output. And then we can also just check the PyTorch summary. You could do print wideNet as well. And you can see that PyTorch is going to give us this nice, neat little representation. This is really useful when you're using somebody else's network to see at least what layers are present and what might we expect the architecture to be. Okay, so we have our function. Now this is also behind the scenes set up some pretty nifty sort of tracking. Remember previously when we had our function where we had several parameters, we needed to manually tell PyTorch that these parameters required gradient calculations, and then we needed to pass them all to our optimizer. In this case, because this is inheriting from nn.module, it knows to keep track of things like sequential layers or different layer types, and automatically take the parameters for each of those. So if we go wideNet.parameters, we'll see that PyTorch can give us back, in this case, a generator, so we need to convert that to a list quickly to see it all at once. This is going to be the parameters, i.e. the weights of the different layers, right? So the first layer has, what's this going to be, 512 weights. The second one is going to have, sorry, let me scroll down through all this. Okay, but the point is the parameters of these different layers are going to be put all together by this parameters function. You can see they already have requires grad equals true. So we don't have to worry too much about that in our optimization loop. So let's jump into that training loop, and you'll notice this looks very similar to the previous optimization loops we did in lesson 1. We're creating our network, which is new. We're defining our loss function, and in this case, we're relying on a built-in loss function, nn.mean-squared-error loss, very similar to the root mean-squared error one that we coded up ourselves in lesson 1. So nice to use a built-in loss function, built-in optimizer, and you could replace this with, sorry, this is wrong. You could replace this with whatever optimizer you'd like to try from the built-in options available. And then in our loop, we're going to do 500 iterations, and each time we're going to zero out the gradients, right? We're going to clear everything. We're going to get our predictions by passing our inputs through our network. We're going to calculate our loss using our loss function. And then we're going to call loss.backwards to backpropagate those errors or those gradients. And then we'll use those to update the parameters via optimizer.step. And then we'll store them for later viewing. So hopefully not too hard to understand, and all ideas that we've seen in lesson 1. And you can see it very quickly learns something quite rapidly, and then it takes a little while longer to get to some sort of optimum loss, or at least it's doing pretty well. So make sure that you understand that code there. This is going to be the same sort of training loop we use again and again going forward. But now that we have this trained network, we can double check to make sure that it is indeed making sensible predictions. So here, this red line is the predictions of our network after it's been trained. And you can see that does capture the trend in the data really well, versus this yellow line, which is just a random untrained network. So that's great. You can go and mess with this some more if you'd like, practice creating maybe a more complicated network architecture, have several hidden layers, play with a number of hidden units in each one, the number of cells, play with the depth, the number of hidden layers, tweak different types of nonlinearity, different optimizers, and see how they go. You don't have to spend too much time, but if you are interested, you could see how simple a network can we do such that it still is able to learn this trend. How complex a network can we do before it stops being able to, or it becomes too complicated or tricky to train. Just mess with it and get a little bit of intuition. Okay, so that's section 1. You can pause the video here if you'd like to do that exploration, or we can carry on in this very, very quick overview of deep learning with PyTorch, which we're using just to build up so that we can make some art, but hopefully is also useful if you're ever interested in taking this further. But yeah, assuming you are ready to move on, let's dive straight into section 2. So once again, I'm relying on some Neuromatch content, which explains this better than I can, or at least I have time to. So do pause the video here and check out this little introduction here. And I'll give a second for you to do that. Pause this video and then resume when you're ready. Okay, so assuming you've gone through this video, you'll see that we get a bit of the history of neural networks. And then we also get this lovely analogy of looking at how the brain's visual cortex works and how it's able to have these sort of different layers where sort of as inputs come in, initially there's neurons that are responding to very specific areas in the visual field and very specific types of stimuli, angles, edges, movement, etc. But as you move up, it's sort of hierarchical. And neurons in later layers in the brain are sort of responding to much wider parts of the visual field, and also a larger variety of stimuli and more complex categories within those stimuli, right to the point where we have an Elvis Presley neuron that might activate when it's anything related to that character. So how can we sort of imitate this in code? The key idea is to use something called a convolutional neural network. So there's a couple of ways of kind of trying to understand and get an intuition for what convolution is. You're welcome to check out, there's some additional resources linked over here, the CNN explainer. But for me, one nice quick way to build a little bit of intuition is this beautiful interactive explorer, which you can go check out on its own website or just play with in this embedded thing here. You can see if we draw an input, right, this is a single channel grayscale image, several things are going to happen. So we can look at this, there's multiple layers, and so we'll break these down and look at them one by one. But this first layer here is a convolutional layer. And what this does is this applies a filter, right? In this case, I think 5x5 filter. And you can see that shown here on the right. Filter, and this one has a sort of diagonal dark line with lighter pixels at the edges. And you can see that as I move my mouse around, different parts of the input image are being fed into this filter. They're being multiplied with this filter and then passed through a nonlinearity. And you can see the result in the second layer, where this second image is bright. That's where this filter is being like maximally activated. The weighted sort of sum is giving a high positive output, right? And you can see in this case, this particular filter is sort of activated for these diagonal edges, right? Diagonal edge on the top, diagonal edge on the bottom, maybe a few on the sides here. So this filter is being activated by specific features in the input image. And in this case, a very simple feature, this diagonal line. Likewise, this filter over here is different. It's kind of picking up the other opposite angle. Some pick up vertical lines or horizontal lines, and some it's less obvious exactly what they're being activated by. And the reason it's not just like this perfectly mathematical result is that these filters are not manually specified, right? No one has gone in and designed these filters to catch these different features. They're learned. These 5x5, this sort of 5x5 filter grid is just parameters that we can learn, that we can train the network. So they start out random, and over time they're able to hopefully learn useful features. And you can imagine how maybe a sort of angled edge might be a useful feature for this network. And so this is kind of a core insight in what we're doing today, that these networks, when given a useful architecture and then when trained well, they're able to learn meaningful representations of the data. They're able to learn useful features, and as we go up the network, more and more sort of concise and expressive features or attributes or dynamics of the image, so that instead of just looking at the raw input pixels, they're able to kind of extract some interesting representation. So that's one key idea, that's this convolution layer. Then you'll notice the next layer is like it looks very much like this first layer but shrunk, and that's exactly what it is. It is something called downsampling or pooling, right? So each block here is the either average or the maximum. In this case, I think it's max pooling, the maximum of 4 pixels in the previous layer, right? And so you can see how this reduces the size from this larger image, right? These filter outputs down to a smaller version of the same. And there's a key thing that happens when you do this kind of pooling, is that now a single feature here, a single number, represents a larger space in the previous layer, right? In this case, only 4 pixels, and those 4 pixels are combined from 9 pixels in the input image. So as we go higher and higher up, maybe there's a second downsampling layer here, we're getting more and more of the image represented by each output. And so this is very similar to that brain analogy where we have more and more of the visual field being activated or being fed into a single neuron. So this is great. We have our data feeding through. We have these learned filters. You can see the filters for the second layer as well. And then to turn all these filter outputs into our final prediction, we need to first of all flatten this out and then create these fully connected linear layers, which is very similar now to the basic network that we saw before, where now every neuron in these hidden layers looks at all of the previous layers' outputs, and the final layer has 10 outputs for the 10 different digits. And by sort of applying this maths, right, each filter gets multiplied by the sort of grid around that location for every point in the image. Then it gets downsampled, then filtered, then downsampled, then flattened, then fed through some fully connected layers until finally we get our outputs. And to score this network, we treat those outputs as like a probability or a likelihood. And you can see in this case, the output corresponding to the number 8 is really high, to the others is really low. And so the sort of first guess of this network, the prediction, is that this is the number 8. If we were to declare this and draw another number, we might see that now the neuron corresponding to 5 is really highly activated and the others are not. If we were to draw something weird, we might see that it's less sure, right? This could be a 7, this is probably a 3, but it might also be some other numbers as well. So yeah, nice little demonstration. You can play around with that to build a bit of intuition. And we're going to see how, again, PyTorch has these different layers built in. And so we can play with them and examine them and feed different images through to get a bit of an understanding of what they do. But we don't have to worry too much about doing the maths ourselves. So let's apply this to an example. We have this data set that was downloaded in the setup section. And if you want to check out the code, you can see that we're using PyTorch's built-in datasets. In fact, they even have datasets.mnist, right, a specific function for this particular dataset because it's such a classic dataset and it's used so often for illustration and research. And so you can see here this data is made up of 28 by 28 pixel images representing different numbers. You can see the labels at the top there. So we're going to try and build a convolutional network to classify these digits. So first building block, nn.conv2d. You can uncomment this line to see the help function for this. So this is going to be what we use to do this convolution operation. And before we define a whole network, we can try this out, right? We can just create this convolutional layer, and then we can pass a single image through it, right? This mnist 0 is getting the first xy pair, and then the first item in that is going to be our sort of x data. And then we have to unsqueeze because everything in PyTorch here is expecting a batch. So without this, we would have a 1 by 28 by 28 image. Adding unsqueeze is going to say batch size 1, number of channels 1, image size 28 by 28, width by height. So we can check the input shape, and then we can see the output shape having fed it through this convolutional layer. So, okay, this is working, that's great. You will notice we have 12 outputs because we specified 12 output channels. And this corresponds to 12 filters that we're going to be learning, each of which has a kernel size of 5, so a 5 by 5 little grid. And then the next thing you'll notice is that we have fewer pixels in this output than the input, right? Our width and our height have gone from 28 to 24. And so there's a couple of parameters that we can sort of investigate here, and the main one is padding. And if you go back to the example, or you think about what that convolutional operation is, we have this 5 by 5 grid, which we're kind of sliding along the image. And so we start with it aligned with the left-hand side of the image, and we slide it across to the right, but it has some width, right? In this case, width 5. So we can't go across 28 times and still be overlapping with the image, unless we pad the image somehow. So if I change the padding from 0 to 2, we're adding 2 pixels around the edge. Now my input size is maintained. But if we leave that at 0, we are getting this reduction in size even without a pooling layer. So that's something worth noting. The other argument that you might be interested in is stride. So the stride is how far across we move this grid, this filter, each step. By default, that's 1, right? We're moving across 1 pixel at a time. If we move across 2 pixels at a time, we're going to be given a much smaller output, because now instead of getting 5 by 5, multiplying this grid and then moving across 1 pixel and doing that again, we're just jumping across 2 pixels in the horizontal and vertical. So changing the stride also affects the output size. But we can leave this at the default, which is stride of 1 and padding 0, and then we should see, yeah, back to the behavior we were seeing right at the beginning. You can play with those parameters and see how each of those affects the output shape. Then we can also examine the parameters, the sort of weights, in this case, of this layer, and these are going to be what we are learning. And notice we have 12 channels, then 5 by 5 for our 5 by 5 kernels, 1 channel. So number of filters, number of channels, width and height. And one very important thing to note, and one key idea behind convolutional networks, is that this number of parameters here doesn't depend on the input image size. We could feed a 200 by 200 pixel image through the same convolutional layer, and it's just going to still be applying these same filters across the whole image. So it only has a limited number of parameters to learn, and it's sharing those parameters across space, across the whole image. So that enables us to learn useful things and not have to learn them at all the different possible locations in the image, and be able to share. It's this idea of sharing parameters across space to reduce the total number of parameters. Very key idea. Okay, so without too much more preamble then, let's actually build a network. We are going to, again, inherit from nn.module. We're going to call this our mini CNN for convolutional neural network. We're creating, in this case, 2 convolutional layers. The first one has 1 channel in, 32 output channels, filter size of 3. The second one is going to go from 32 channels to 64 channels. Then we're going to define a couple of linear layers as well. And finally, we'll use max pooling to do this downsampling operation. Now you'll notice, unlike the previous example, I'm not using nn.sequential here. You could construct this network by using nn.sequential and then passing in all your layers, and then your forward method would just be exactly the same as previously. But there's another sort of convention which I'd like to highlight, and so in this case we're just creating the bare minimum layers that we'll need in our initialization function and putting the meat of it in our forward method, right? And so this is going to define the actual flow of data. So we're going to get in an image, we're going to pass it through our first convolutional layer, then through a nonlinearity, right? f.relu is that rectified linear function, then through our second convolutional layer, then through another nonlinearity, then we're going to apply some pooling, then we're going to flatten everything out, and then apply it through our fully connected layer, a nonlinearity, and then our final output layer. And that's going to give us our 10 outputs, which is going to correspond to the digits. So there's many ways you could do this. You could add more convolutional layers and pooling layers in whatever order you like. This is just one example. But let's train this network and see how it does, and then as an exercise you're welcome to come back and modify that architecture to sort of suit you. So one thing that's different here, we can't push all the images through in one go, right? We can't just feed all the data through. So we're going to split it up into batches, and this is where gradient descent becomes mini batch gradient descent or stochastic gradient descent. And we're going to handle this in this case using PyTorch's data loader functionality. So we don't have to worry too much about creating those batches ourselves, but you could just as easily, in a sort of secondary loop through all of your data, putting chunks of it through the network at a time, and after each batch we update the weights, so that we're not waiting to go through all of these thousands of images, then do one update. We're going to do an update every time we put 16 or 32 or 64 images through. So this is defining our data loader, right, which is taking our data set, chunking it up into batches of size 16, and handling some other neat little functionality behind the scenes. Then we're creating our model. We're sending it to the GPU, right? If you see to device, we're saying to GPU. Device is defined earlier in the notebook. We're defining our loss. Now, because this is a classification task, we use a different loss, cross-entropy loss. You can think of this as a nice, smooth, differentiable version of accuracy, right? Where we treat the outputs as probabilities and we penalize it for wrong predictions, but in a differentiable way, rather than accuracy, where you can imagine if you get 23 right and then 24 right, there's no gradient that we can work with there. So creating our model, creating our loss function, creating an optimizer, and we just say, again, model.parameters, and it's going to know that it can look at the different trainable parameters of all of these different layers that we define in the network. So it's going to handle all of that for us. And then in our training loop, we're going to run through all the data only twice, because we've got lots and lots of data to work with now. And then for data and target this is just a progress bar, but in our train data loader, right? So this is going to get a batch of inputs and a batch of targets. We're going to make sure those are also on the GPU. We're going to zero out our gradients. We're going to run the data through our model to get our output. We're going to calculate our loss. We're going to backpropagate those gradients, and then we're going to update our parameters. So again, it's very much the same training loop that we keep seeing. There's a few different nuances each time, but this core idea, we feed some data through, we look at the loss, and specifically how do we change our parameters to reduce that loss, and then we use that information to update our parameters, and then we repeat again and again and again. And if we run this code, we'll see it takes a little while. It's feeding thousands and thousands of images through our convolutional neural network. And then once it's done, we can examine this network, see how well it does. And by the way, if you're curious, you can remove all of the two device lines in this. So just remove each of these and see how long it takes on the CPU versus GPU. And you'll see why we often like to work on the GPU. It's able to do, especially operations like convolution, very efficiently in parallel. So, little something for you to try there. And then, as a quick little demo, because we're not focused on image classification in this course, we just want to move on and get these basic ideas. But let's quickly just evaluate this network. We've trained it. How do we tell how well it's doing? Well, we could look at the loss. We could record the losses over time and view that. Or in this case, we're just going to go through our validation set. So this is different images that we didn't use for training. Create a test data loader out of those, and then iterate through that without needing to track gradients. So that's why we have with torch.nograd. You could also call model.eval, which is going to put it in evaluation mode. Then we're going to run through our data. We're going to get our predictions versus the actual labels. We're going to, now these predictions are going to be like probabilities or the sort of raw outputs, 10 values. We're going to turn that into our like predicted labels by using the argmax function. So this is going to say of the 10 outputs, which is highest, and that's going to be our actual label. We can compare those to the true labels and keep track of how many match and print that out. So if you've got any questions about this code, feel free to ask on Discord. But yeah, we're just running through our data, our test data that the model hasn't seen before, and we get an accuracy in this case of nearly 97%, which is not bad. You can do better, right? We just this is a fairly arbitrary network architecture. I just put it together to show these different layers. So you're welcome to go back, train for more epochs, use a different learning rate or a different optimizer, create a different architecture, see how good you can get. But that's for those who are interested. For now, we're going to take a deep breath. This is where we took a break in the live lesson. So if you would like to pause the video, go get a cup of tea, can highly recommend. But we've managed to cover a good chunk of what would be probably the first week or two of an introductory deep learning course. So congrats, well done for bearing with us through that. There's lots of resources if you'd like to learn more. I keep talking about Neuromatch because I've just helped teach that recently, but there's plenty of other great courses online. If you'd like to learn to actually apply images for, deep learning models for image classification and many other tasks, and you prefer a top-down approach, highly recommend the Fast AI course. Incredible, incredible material. But for now, we're going to now move away from defining our own networks and training them, and we're going to say, we keep talking about how these networks learn great representations. What's one thing we can do with that? So we're going to use a network that's already been trained for us by somebody else, and we're going to use that for an artistic purpose. So let's move on into section 3, style transfer. Okay, so we mentioned that these networks learn useful representations or features, and we also mentioned that it's hierarchical. So if we look at this architecture here, this is the VGG16 network. We sort of had the idea that at early layers, right, these first convolutional layers, it's going to learn very simple features, right? Those filters are going to be looking for edges, colors, gradients, basic shapes and patterns, right? And as we move through, maybe it's now curves or corners, right? Slightly more complicated patterns. And as you move deeper and deeper, we're getting now out of those basic ideas into structure and position across the whole thing, larger concepts like eyes and noses and wheels and trees and grass, textures, ideas. And as we go deeper and deeper and deeper to the end of this network, we end up with its original outputs, 1,000 different outputs, and those are the ImageNet classes. So this was trained on a data set called ImageNet, 1,000 different classes of image, right? It could be a sea snake or a Labrador or a tractor or an aeroplane. So lots and lots of different images from the real world. And this network's been trained such that it does pretty well at predicting those classes. But we're not interested in identifying aeroplanes versus Labradors. We're just going to abuse this network for our own purposes. So we can load up the network like so. And if you uncomment and run this next line, we're just going to see the summary, just like we saw the summary of our simpler networks earlier. But in this case, this network has many more layers. Now, this is still a small network by today's standards. Some modern convolutional networks have maybe 200 layers, so they can be really complicated. But this, for our purposes, is already going to be plenty enough for what we want to do. And often they're named, or they have at least some way of sort of denoting them. And so we're going to try and use the outputs of different layers to measure things like style and content of an image. Okay, so don't worry, we'll work up to this. So the first step is to say, okay, we'd like to look at the representations at different layers. One way to do that is to feed in an image and to see which neurons are activated. So to look at like the outputs of specific neurons or specific points, or just the output of these different layers. And so to do that, I've borrowed code from a great resource here. If you look at the code and see what it's actually doing, it's not too crazy. We're just creating our own sort of network based on this VGG network. And we're going to run through the layers. And if that layer is one of the ones that we're interested in, we're going to keep track of the outputs. And then at the end, we'll return those outputs. So nothing too complicated, but don't worry too much about it. Let's try this out by example to see exactly what's happening. So I've downloaded a few images here. A pretty cat, this is going to be our content image, right? We'd like to keep the overall shape and content of this one, but we'd like to try and capture this style. So how do we do that? How do we extract these features from the network? And then later, how do we use them? Let's test this out. So first of all, converting the image to a PyTorch tensor. Now, one little modification I recommend making here. We are going to end up with batch size, number of channels, width and height. If it's a PNG image that you're using, you might have 4 channels, and we only want the first 3 channels. So I'm just going to do this little indexing thing here, and you could do this in many ways, but I want to make it explicit. We want everything in the batch, but only the first 3 channels, then the width and the height, so that if you're loading in a PyTorch, a PNG image with transparency, you won't have issues, right? Not strictly necessary for the demo, but nice to catch that bug if you are trying to run this on your own pictures. So how do we get the internal representations? Here we are going to turn our content image, which is a PIL image by default, into a tensor. We're going to create a feature extractor, right, that class we defined earlier, based on that VGG network, that pre-trained network that we also loaded earlier. And we're going to say we're interested in these 2 layers, right, layer 15 and layer 19, which in this case are, I wanted layer 14 and layer 19, doesn't really matter, but these 2 convolutional layers somewhere in the middle. Now it doesn't hugely matter, but let me actually just fix this, layer 14 and layer 19. And then let's take a look at the outputs, right? The outputs of these layers. We have a list with 2 different tensors. This one has the outputs of layer 14. This one has the outputs of layer 19, right? So this is great. We can extract these features, and that's what we want. Likewise, for the style extractor, we're interested in some of the earlier layers, because the idea here is that things like style, the sort of shapes and painting style, if you will, are going to be better described by some earlier layers, whereas the overall structure might be better captured by some of the later layers, which won't be looking so much at simple features like edges and patterns, but more overall arrangement. So we're creating a style extractor very much the same way, specifying a few layers. Now I should mention These layer numbers are completely arbitrary, right? I've seen many different tutorials, each of which seems to have their own preference. So that's totally something that you can experiment with and explore to find what works best. So the idea is that we feed in an image and we get back these tensors, which are the outputs of the different neurons in the network, the different layers in the network. How do we use this to define a loss function? Well, we talked about saying we want the same sort of content as the content image and the same sort of style as the style image. So if we start with the content, what that might mean is that we expect similar outputs from those content layers that we're looking at for both images, right? So we have our target content features. We're going to do the same thing and use our same extractor to get the outputs of those layers for our... Ooh. Sorry, that noise that you're going to be hearing is the very first rains. We've had a long dry winter and then now dry beginning to the summer. So this is a very exciting time in Zimbabwe. The first little bit of rains in usually the beginning of October makes everyone happy, and everything goes from being brown and bare and dry and dusty to lush and green in a couple of weeks. So yeah, sorry if I'm distracted, but that's a very happy sound. I just hope it doesn't mess with our audio quality too badly. Okay, so we're trying to measure how similar two images are in terms of content by looking at the outputs of those layers with our content extractor. So we have our target features, we get the same features for our input image, and then we're just going to run through in that list each of those layers outputs. We would like to compare them, and so we're going to take the L1 loss. You can think of this like the mean absolute difference, the mean absolute error between the features of our image and the target image or the content image. This zip function here is just saying take the first item in this list and the first item in this list and kind of feed them together, and then the second and the second and the third and so on. So there's a few ways you could implement this. Don't worry if this is unfamiliar. We're just saying for every set of features, right? For every set of features in this list that we get from the feature extractor, take the mean difference between these features from the content, like target, and our image. So that's not too bad. We can try this out, create a random image, and measure the loss between this random image and our target content, and we get some number back. And importantly, this is differentiable because that whole big network is all defined with things that are PyTorch operations, which we can then backwards propagate our gradients through. Okay, so that's content loss, nothing too crazy there. The style loss is a little bit more interesting because we do care about the same sorts of features being activated, right? We want the same sorts of styles and patterns, but we don't necessarily want them in the same parts of the image because otherwise we're just trying to copy the style image directly, as opposed to using that same style but on our new image, on new layout. So to get around this, we don't use the L1 loss or mean squared error loss directly. We first calculate something called the gram matrix. And I haven't seen amazing explanations as to why, but the intuition that I sort of recommend, or at least that I use, is that by calculating this gram matrix, we measure which features, which features are present, like which filters are being activated and so on, but we decouple them from the absolute position in the image. So we're taking our input, we're creating, sort of reshaping it and then multiplying it with a transpose of itself. This little extra scaling factor here is so that large matrices, i.e. the outputs of earlier layers, aren't going to overwhelm the total loss and have an outsized effect. So this should be maybe called the normalized gram matrix or something. Anyway, it's a little bit technical. You'll see different versions of this implementation. This is just my take on it, with inspiration from elsewhere online. Once you get past that one sort of extra step, it's very similar to the content loss. We're getting our style features with the style extractor, so these are just the raw outputs of those layers. Then going through, comparing these with the target style features, except that instead of comparing them directly, we're taking the gram matrix of both, and then we can compute the difference, or in this case the mean squared difference between them, and add that to our loss. So it's slightly more nuanced, but in this case it does still give us a measure of stylistic similarity. And because we're taking the gram matrix, it's not one that's just, does this look exactly like the input image in terms of position and everything else? It's more like which types of features are coming up. So I hope that's enough of an explanation. Now that we have our measures of loss, how do we wrap this together? How do we actually generate an image that has this desired property of the content image and the style of the style image? So we're just going to do yet another optimization loop, right? And this is going to look very familiar from the previous training loops and the previous optimization loops last week. Once again, we're going to be optimizing direct pixels in this case. So we're creating an image, and in this case, we're basing it on the content image so that we start from that useful point and we try and move it more and more to match the style of the style image. You could also start from random, or you could start from the style image, something for you to explore. Right? So we create our set of parameters, we tell PyTorch to keep track of the gradients, we create our optimizer and tell it what parameters to operate on. We are going to use some weights, some sort of special parameters to say how much we weight or value the content loss versus the style loss. And then over some number of iterations, we're going to, once again, zero out the gradients. We're going to calculate the style loss, right? So how well does this match the style of the style image? And multiply that by the style weight. Then we're going to calculate the content loss and multiply that by the content weight. And the loss is going to be this sum of these two values. So when we call loss.backwards, it's saying what's the gradient of the combined loss with respect to each parameter. So you're going to try and optimize for some combination of both of these losses. And this is a really useful technique. You could use either one of these losses or both of these losses along with a different type of loss, for example, loss via clip. And in general, you can add multiple different objectives and just sum them in like a weighted sum to kind of control what kind of output you're looking for. So really useful technique there. But besides this sort of difference of having two different losses, everything else here is exactly the same as many other optimization loops. Zero the gradients, calculate the loss.backwards, optimizer.step. And so you see this is a really powerful approach, right? And in this case, occasionally showing some output and keeping track of the losses over time. So let's run this cell and see what it does. Here's our original image, our content image. And our loss is fairly high, loss of 44. One sort of thing you'll notice with the style loss is it starts out really high, but it very rapidly drops. Okay, and then this is after, I think, 25 iterations. You can already see it's starting to get more of the kind of structure and appearance of our style image, right, which is up here. Sort of a cool acrylic pour by the look of it. Not too much longer to go, our loss is continuing to decrease. And there's the plot of the loss, and we could look at our final output image. Let me just copy the code. Yeah, so let's take a look at the final image. And sure enough, we have something that looks, to me at least, like the content of the original image with the style, at least a little bit of the style, of the style image. So yay, success. We are able to exploit the learned representations of that pre-trained network to our advantage. Cool, so that's really neat. I know that it's not ideal to have everything spread out over multiple cells and so on for these different loss functions and which layers are being looked at. So I've got a slightly tidier version here. We're downloading a new style image. Oops. And then in the cell, I've just specified certain things as parameters so that it appears as a neat little form. You can control the style image, the content image path, the width and height, the content layers and style layers. Highly recommend trying different combinations there. The learning rate, the style weight, the content weight. We are adding some image transforms to kind of smooth things out and doing, in this case, a batch of 4 different transforms each time we calculate the loss. But that's, again, something you could play with. And we can see in kind of real time this time how our image morphs. And yeah, to me at least, looks like it's doing an okay job of taking the content of this image and the style of that image and producing some sort of combination. So once again, to highlight, this is just me trying to create a fairly clean style transfer implementation. All of it is completely thumb-sucked. There's no deep research that's gone into choosing these parameters at all. So I wouldn't necessarily recommend this as the best style transfer on the internet. Nothing like it. But if you go, and we did this in the lesson, if you go and look at other examples, style transfer, PyTorch, collab, just pull up a random a random example or demo, if you look through the code, you'll realize that although their actual implementation might be really different, the idea is going to be very much the same, right? They have some way of loading images, they have a way of showing images, they have a content loss, which is, in their case, mean squared error between the input and the target. They have a style loss, which also involves the gram matrix. They're loading, in this case, a slightly larger model. They're doing some normalization, which we should probably have done. Defining their content layers and style layers by the names of the layers in the network. And then, yeah, some big method to combine the two losses, running through the different defined layers to get the outputs, calculate the gram matrix, and so on. And then doing the gradient descent for some number of steps, zero the gradients, get the pass the input image through their model, which is handling all of the different loss calculations, get some sort of combined score, right, of the style loss and the content loss, run lost backwards, and then run optimizer.step. So very much the same approach, even if the code looks very different. And hopefully you could read this and adapt it and know what we mean when we're specifying different content layers or using different networks or tweaking the content loss and so on. Now that you know what's happening behind the scenes, hopefully you can take that and modify it. Great, so that's the end of the bulk of this lesson. Just like I did in the real one, I will give a very quick overview of the final sort of bonus sections. But I think this that we've covered so far is already a hang of a lot of content and breadth, so well done for getting through it. Don't worry if it seems a little bit overwhelming. I think that's a common feeling, right? And totally understandable, because I've just given you a huge amount of content really quickly. It's going to take time to settle in. Don't worry about that. But hopefully at least the core ideas that we can put together these architectures that use some interesting tricks to learn useful representations. They're able to sort of do image classification really well, and as a byproduct, we can use them to our advantage for artistic purposes, like making a cat that looks like it's made out of fire. But yeah, hopefully you can see the utility of that, and also you're less intimidated when you see a PyTorch model and you load it and you realize it's got all of these crazy layers. You know that these are just built-in building blocks. We can understand these, we can examine the documentation for them and see what they do. And by chaining them together one after the other, we can achieve some pretty complicated feats of deep learning. Anyway, so I hope that's useful. Yeah, we're just going to take a quick look at the bonus sections, but those will also be kind of recapped at the start of next week when everyone's fresh. So don't worry too much about the bonus sections this week. Okay, so bonus 1, autoencoders, learned representations, and variational autoencoders. So the representations we keep talking about in the previous case were things that the network learned, right? Those filters and its convolutional layers and so on, that were useful for the end task, which in that case was image classification. If we're interested in image generation, we get a different sort of set of constraints, and we can, it turns out, come up with an architecture that forces the network to learn a useful representation for image reconstruction. And hopefully we can then use that for image generation. So this little diagram here, I think I put the source in somewhere, I might have to add that, shows a very basic autoencoder. We're going to take in an image, we're going to apply the same sorts of layers as we've been seeing, convolutional layers, pooling layers, etc., down to some sort of bottleneck, right? Somewhere here there's a layer with 10 outputs. And this is going to be our hidden state or our internal representation or our latent representation, H or Z. Then the second part of the network is kind of going to be the inverse of the first. Oh, love this rain. Sorry about the audio. I'll get through this really quickly and then we'll be done. So we're going to try and go back from that set of 10 numbers, those 10 outputs, back up to a full image, right? And this deconvolution is just kind of the inverse of the convolutional layers here. So we can make a network like this, we can feed an image through, and then we can calculate a loss based on how close its output looks to the input. So we don't need labels, we can use any images we like. And the idea here is that to do this task well, it has to learn how to go from the image to a relatively small amount of numbers, and how to go from that small set of numbers back up to the image. right? So we're going to create this same sort of idea ourselves. We're going to use a hidden dimension size of 20. You can change that to your convenience. And so we're going to set up some layers just like before, a couple of convolutional layers, some fully connected layers. We're going to set up the decoder layers, right, that second half of the network, which use, again, a couple of linear layers, and then this conv transpose 2D is like this deconvolution operation, right? It's like the inverse of convolution, if you can think of it like that. Then we're going to split up our forward paths into encoding the image, first of all, so going from the image down to that hidden dimension, and this final fully connected layer, FC2, if you notice it has this hidden dimension size output, so 20 outputs. Then the decoding step is going to go from that those 20 outputs, going to go back through these deconvolutional, or these decoder layers, the linear layers, and deconvolutional conv transpose 2D layers, back up to the original image size. So having defined this network, we can try this out. We can encode an image, right, just the first image in our MNIST dataset, and see that its shape is size 20, batch size 1. We can decode that encoded image and see that this goes back to being the same size as the input. And in this case, because we haven't trained it yet, the decoded output is just random noise, right? It doesn't look like anything in particular. So to train the network, we need to actually run it. I stole this code from the Neuromatch page, which taught autoencoders and variational autoencoders really well. I'd recommend that if you're looking to go any deeper than a surface level into this. But again, we have we have our autoencoder, we have an optimizer on the autoencoder's parameters, we have a loss function, right, mean squared error. We're creating a data loader, and then for some number of epochs, for some number of batches, we are zeroing the gradients. We're running the forward method, which is going to encode the image and decode it again. We're going to do our loss function comparing the reconstruction to the original image, loss.backwards, optimizer.step, and apply and sort of track our loss. And after training, we can then plot some reconstructed versions of some images. So this is going to be the image, and then we're going to encode it and decode it again and see how close it is to the input image. It's going to take a little while to train. And why are we doing this? So this is really useful for all sorts of things, right? You can imagine for compression, you could train a good autoencoder. Instead of storing a whole image, you could store just the hidden representation, and then later, if you wanted to recreate that image, you just pass it through the decoder. And this is in fact used for all sorts of things. Some really low bandwidth audio codecs use a really good autoencoder to take your high fidelity audio and compress it down to some really small hidden representation for every sort of time step. And then at the receiving end, all you have to send is that hidden representation because it has a copy of the decoder and it can recreate that audio with really high fidelity. So really useful for compression and similar tasks. But also our hope is that once we have an image with a decoder that can go from 10 random numbers to an output image, maybe we can use that to generate new images, right? By tweaking that hidden representation or by creating just random sets of 10 numbers or 20 numbers. We can then feed that through the decoder and hopefully get a useful image out. So we'll test that out shortly. Let me just wait for this to train another 10 seconds. Great, and so this is our trained autoencoder, taking this image, shrinking it down to this hidden representation, just 20 outputs of a layer, and then decoding that back into an image. And you can see the reconstructed images look impressively like the originals. So let's generate some new images, right? Let's generate some hidden representations and decode them, just random numbers, between 20 random numbers. And what we see is, instead of some nice digits, these kind of weird garbled shapes. And so the difficulty here is that we haven't really constrained what this hidden representation, these 20 numbers or 10 numbers, look like. We've just said, here's your task network, go from an image to this hidden representation and back. But because there's no constraint, what it ends up doing by default is separating the different classes quite drastically within this latent space. So it's a little bit of a weird concept. Again, we're not going to go too much in depth. The solution to this, if you want to generate plausible images for any random input to the decoder, you need to constrain this hidden representation somehow. And we do that by applying an extra component to the loss that says we don't want this hidden representation too crazily distributed. We want to sort of enforce some general distribution on it. So again, a little bit tricky. The maths is a little bit too much for us to cover in this art course, but I highly recommend reading the Neuromatch material if you're interested in it. And the key thing for us is that that's the difference between an autoencoder, which is really good at reconstructing images that you feed in, and a variational autoencoder, which is not only good at reconstructing the input image, but also generating a new distribution of images that look similar to the training data, whereas these don't look anything like the training data. Okay, so that's a little bit of background. It gives us this idea of the latent space. We'll recap this at the start of next lesson. For now, let's use our really bad autoencoder to end, as is going to become a tradition, with a bit of clip fun. So we're just going to quickly write some code to decode a bunch of random Zs or Hs and create these strange looking glyphs, stack them all on top of each other in a sort of randomly scattered arrangement. And then we're going to pull in clip. We're going to define our clip loss, which is going to compare this image to a text prompt. In this case, I've given it the prompt skull and bones. This is all stuff from lesson 1. If you're curious, I'd rather go look at that than try and understand it here. But what we're going to do is we're going to create some image with 500 of these random glyphs scattered at random offsets. We're going to mess with the Z values. So we're going to be optimizing not the raw pixels of the image, but the hidden representations, which are then fed through our decoder, right? If we look at the, where is it? Get out image function, right, is using the decoder of our autoencoder to generate a 28 by 28 pixel image from 20 random numbers, or 20 numbers. So we're going to be optimizing those 20 numbers, and that's kind of the key trick here. Rather than optimizing the image, we're optimizing the input to some sort of generative model, right? And in this case, it's not a very good generative model, and it's also not ideal to just randomly stack them all together, but it does work. And at the end of the day, we'll get some image that, if you watch the video, in fact, you'll see it starts out with these kind of randomly scattered random glyphs, and over time, each one kind of morphs such that, as a whole, that looks kind of like skulls and bones, at least to a certain kind of generous interpretation. So not a particularly useful algorithm at the end here, but a fun demonstration that whatever wacky generative network we create, we can then use that in combination with other approaches and techniques to do whatever we want. You could add a content loss to try and make it look like some content image. You could add a style loss to try and make it look like some style image. You could add multiple clip losses such that it matches different prompts. Really, the sky's the limit. I wouldn't recommend trying to go too far with this particular implementation, but it's fun. It's fun that we can go and just optimize some, in this case, what is this? Like, we have 500 by 20, so 10,000 random numbers, which in batches of 20 get fed to some autoencoder's decoder, and then the outputs get stacked together randomly, and we end up with some image. Yeah, so fun little demo, I hope. Not particularly useful in its current incarnation, but nice as a stepping stone to next week. Next week we're going to look at the next step on from variational autoencoders, which is GANs, right? How do we train a network to learn how to produce really plausible images? And it's going to build on the idea of these autoencoders, but with a different method of training. And then we're going to use that same idea, optimizing the latent representation of that GAN to create some really cool outputs. So I hope you found this interesting. If there's questions or comments or mistakes that you noticed, do put them on the Discord. Feel free to ask in the Lesson 2 channel so that we know that it's specific to this lesson. I will be linking the original notebook in the video notes, and you'll also find it linked in the Lesson 2 channel on Discord. Yeah, I hope you enjoyed this. If you have feedback on the style or the content, that's also much appreciated. This is very much version 1 of this course, so I'm sure there's lots of ways we could improve and change the order of things and the different concepts. Yeah, so please, any feedback is much appreciated. But I will see you next week when we will play with GANs. Until then, cheers.